asset maintenance through lubricant condition monitoring. And we are privileged to have Stephen Lumley, the technical manager from Wearcheck. They're basically condition monitoring specialists in South Africa, but of course with branches around Africa. So we'll be talking about lubricant condition monitoring, per se, looking at especially how it affects our assets in terms of performance and maintenance. So allow me to give Stephen just a minute to introduce herself. I'll ask her one question and then she can take it up from there. Welcome, Stephen.
Thank you so much, Doctor. Miriam sort of thrust me into the limelight while you were reconnecting. So
Okay.
I have sort of introduced myself to
Okay.
hopefully to the viewers who are out there. I did explain what my role is at Wearcheck as technical manager. But I can elaborate a little bit on that. So I tend to get involved in research and development of new products and services, training. I tend to get involved in the diagnostic department. So at Wearcheck, I wear a number of different hats underneath the guise of technical manager.
Okay, welcome so much. So my first question is, I think let's start from the fundamentals. What is a lubricant and how central is it towards affecting the asset maintenance and performance? And I pick it up from there, then you can go forward.
Thank you, Doctor. So, suppose to a lot of people, a lubricant is just a line item on an invoice. But to me, a lubricant is a marvel of petrochemical engineering. It's a complex blend of different base oils and additives that are formulated to perform specific functions in very specific applications. Functions like reducing friction and wear, dissipating heat, acting as a structural material. And as such, they play a pivotal role in ensuring the longevity and the performance of mechanical systems because they are a functional component, just like a piston is to an engine or a gear assembly is to a transmission. And that's important to view lubricants as a functional component, not just something that gets added to a system. Proper lubrication is often the biggest determinant of equipment uptime, maintenance cost, energy conservation, and overall asset reliability. And think of it this way. Could the human body survive without blood? Of course not. Blood circulates life-sustaining oxygen, it removes waste, it regulates temperature, and it supports immune functions. Similarly, most mechanical systems can't survive, let alone operate optimally, without lubricants, because ultimately a lubricant is the lifeblood of a mechanical system. And that is what I'm hoping I will be able to impart to everybody. So I am now going to start sharing my presentation. Right. So before we delve into the technical details, here's a quick overview of what we're going to be covering today. I'll start with a brief company overview so you understand who we are at Wearcheck and what it is that we do. Then we'll talk about what oil analysis is because it is often misunderstood and underestimated. We'll explore the objectives of oil analysis, the value it brings to maintenance and reliability, and ultimately how it helps us move from reactive to predictive maintenance strategies. I'll also introduce some of the different maintenance philosophies that are out there. And finally, we'll wrap up the section by discussing the various functions that oil analysis serves across different industries. So let's begin by looking at who Wearcheck is and how we've built our expertise in the condition monitoring field. So as James pointed out, we are condition monitoring specialists with specialized divisions that focus on different areas within the broader field of condition monitoring. So for example, there is our ARC division or asset reliability care. These guys do things like vibration, thermography, ultrasound, operating deflection shapes, motion video amplification. Then there is our advanced field services division. these guys tend to dabble in the more exotic types of non-destructive testing. So things like pressure vessel testing, ultrasonic dye penetration, magnetic particle resonance. They also do things like technical compliance and road condition monitoring. Then there is our LUR division, lubrication-enabled reliability. And these guys are all about looking after your lubricants the way they should be looked after. So we're talking about filtration, dispensing, storage, and also sampling. We also provide quite a bit of training for the different services that we provide to our customers. So things like oil analysis, vibration, thermography, alignment, and balancing. But I suspect the service that most people associate Wearcheck with is analysis of fuels, coolants, transformer oils, AdBlue, water, but more relevantly, the scientific analysis of used oils from mechanical systems, which we test in one of our 16 laboratories. So we process oil samples from different industries and machines around the world. Everything from diesel engines running on an American military base in the Middle East, to the wind turbine gearboxes in South Africa's largest wind farms, to the jet engines in the South African presidential fleet of Dassault Falcon jets operated by our South African Air Force's Squadron 21, all come to Wearcheck. Now, why am I telling you this? To brag? Yeah, maybe a little bit. But the main reason I'm telling you this is because when you are processing over, what is that, almost 900,000 oil samples a year, you gain a powerful advantage: data. That volume of samples gives us insights into tribological and oil-related trends, anomalies, failure patterns across various machines and various lubricant types, and often before the machine even shows symptoms. Because you see, lubricants aren't just consumables. They are a diagnostic tool, as they often experience everything that the machine experiences. So hopefully that little introduction gives you some context or flavor as to where I'm coming from. So let's jump straight in. What is oil analysis? So oil analysis is a scientific discipline that sits at the intersection of chemistry, tribology, which is the study of friction and wear, material science, and mechanical engineering. The analogy of an oil sample being to a machine what a blood sample is to a human is often used, and with very good reason. The processes used in both disciplines are very similar. So just as blood circulates through the human body, carrying vital information about your health, oil circulates through a mechanical system, carrying valuable insights about the machine's condition. A blood test can reveal things like infection, organ function, or inflammation. Likewise, oil analysis can detect things like wear, contaminants, oil degradations, and other warning signs of mechanical stress. In both cases, a very small sample can tell a very big story. In the case of a blood sample, it could save your life by early detection of a life-threatening condition. In the case of an oil sample, it could save your machine and your operation, going back, by basically catching a failure in your machine. So it could save your machine, it could save your operation by literally catching a fault before it literally turns into a failure. So what do we do with all these oil samples that people send us? Well, we subject them to a variety of different tests to determine the three main objectives of oil analysis. So we want to be able to monitor the condition of the mechanical system in terms of the wear and tear taking place. We want to be able to monitor the condition of the oil, and we also want to be able to detect and monitor contaminants in the oil. Now, the types of tests that are performed depend very much on the application and what within that application we're trying to detect. But what you see on the screen here are some of the more common tests that get performed on routine oil samples that we would typically receive from the mining industry, agriculture, construction, and the transport sector. Once the laboratory tests have been completed by the lab, the results, along with the customer supplied information about where the oil came from, is sent through to a diagnostic team who review the data within the context of the customer supplied information, and they provide a diagnosis that contains observations and recommendations. So in a nutshell, what we do is basically mechanical pathology. So I'm going to talk a little bit about the value of oil analysis, and I'm going to introduce the concept of the PF curve. The PF curve is basically a visual representation of how an asset or a machine's condition basically worsens over time, from the point when a fault first starts, but is usually still hidden, to the point of complete failure. So P denotes potential failure. So this is the point when a fault can first be detected. The machine is still working, but signs of trouble are starting. F denotes functional failure. So this is when the equipment can no longer do its job. The asset has failed, and you either need to repair it or you need to replace it. So the PF interval is the time between the potential failure and the functional failure. And it stands to reason that the earlier you detect a problem in this window, the more time you have to plan and respond to a potential issue. Now, the reason this is important is because, quite frankly, early detection saves money and prevents unplanned downtime. Unlike other condition monitoring techniques, for example, like vibration, which detects failures or faults later through mechanical changes, oil analysis provides an early warning within that PF interval. So here is a different visual representation of the PF concept and how it might potentially play out in practice, from a healthy machine to a potential failure, and finally through to a functional failure. And I've overlaid the detection bands of the different condition monitoring techniques so you can see where they would kind of play within a fault on, for example, an engine. Now, oil analysis has the ability to detect the subtle chemical and wear-related, let's call them clues, before mechanical changes are visible. And this makes it a frontline defense when it comes to predictive maintenance. And it's for this reason that the vast majority of original equipment manufacturers have routine oil analysis programs as part of their overall maintenance and also warranty strategy. So to understand where oil analysis fits in into the bigger, let's call it maintenance picture, it helps to kind of zoom out and look at the broader philosophies. And these philosophies are often guided by, for example, reliability-centered maintenance, which helps match the right maintenance strategy to each asset. So a breakdown maintenance, this is run to failure. This is like driving until your engine seizes. It's acceptable for non-critical or low-cost assets, but not the best way to handle very expensive equipment. Preventative maintenance, this is time or usage-based. So that would be the equivalent of, let's say, for example, changing the oil in your engine every 10,000 kilometers, regardless of whether it's needed. Reliable, but could be wasteful. Then there is predictive maintenance, which is condition-based. So we're going to be monitoring for signs of trouble and acting when needed. This is where oil analysis shines, by detecting wear, contamination, and oil degradation earlier on. Then you have proactive maintenance. This tackles root cause, not just symptoms. So oil analysis can also help here. So for example, by being able to identify a reoccurring contamination issue within a machine that potentially leads to better filtration or improvements on a sealing system. So oil analysis plays a key role in both the predictive and proactive strategies, which makes it a vital tool for any reliability-focused maintenance program. So let's tie this back to the human body. If a machine's oil is like its blood, then each maintenance philosophy is like a different approach to healthcare. So let's use the human heart as an example. So breakdown maintenance, this would be like waiting for a heart attack before doing anything. Very expensive, very disruptive, and incredibly risky. And I'm sure I don't need to say fatal. Preventative maintenance is like replacing a heart valve before it fails. So even if the patient feels fine, we still want to be very cautious. So it's done based on risk factors and the probability of failure, not necessarily symptoms. Predictive maintenance is like going for a routine checkup where non-invasive tests like blood sampling or electrocardiogram is done. So in the case of an electrocardiogram, we're trying to measure the heart's electrical activity. These tests can spot early warning signs like high cholesterol or inflammation of your heart, so you can act before a serious problem or heart attack occurs. And then proactive maintenance goes one step further. It's like changing your lifestyle to avoid issues altogether. So better eating, sleep, less stress, which I'm sure none of us probably do as much as we should. But in machine terms, it means eliminating the root cause of failure. For example, like poor filtration, incorrect lubricant use, or even poor maintenance practices. So now that we've placed oil analysis in the broader, let's call it maintenance landscape, let's look at what that actually translates to in practice. What benefits does it deliver when used in the predictive and in the proactive mode? So this slide kind of breaks it down side by side. In the predictive mode, oil analysis helps us catch problems early. It reduces the severity of the failure and allows us to plan maintenance activities more effectively. It's about timely interventions. In proactive mode, the focus shifts to prevention, using the data to understand why issues keep happening and making changes that reduce the failure rate altogether. So it's not just about fixing the machine, it's about improving the systems that support the machine. And in both cases, the goal is the same: reduce downtime, lower maintenance cost, and ultimately better reliability. So now that we understand the objectives of oil analysis, the three main objectives, which were to detect abnormal oil degradation and contamination, let's break it down into specific functions that oil analysis helps us achieve. So these 9 blocks here basically summarize let's call them key outcomes that one could expect when oil analysis is used effectively. So we want to be able to detect abnormal wear, oil degradation. We want to be able to detect contamination, impending failures. We want to also be able to verify the oil in use, optimize service intervals, avoid unnecessary overhauls if at all possible. We really want to avoid loss of production, and ultimately we want to save money. So over the next few slides, we are going to take a closer look at each of these, what they mean, how they work in practice, and why they matter to reliability and cost savings. But first, so now that we've elaborated on the types of things that we do, we're going to look at the first function of oil analysis, which is to detect abnormal wear. So how do we do that? Well, the metallurgy of particular components is known, or we can find them out by engaging with the manufacturer. So, for example, we know that pistons are made of aluminium alloys, plain bearings contain lead, thrust washers and bushers usually contain things like copper, and shaft gears and roller bearings usually consist of different alloys that contain iron. So we're looking at steels. But if we say we can detect abnormal wear, this kind of implies that we know what normal means, what normal wear is. So what is normal wear? And what does a normal machine look like? And here's where things start to get a bit more complicated, as what might be normal for one machine might not be normal for another, because each machine operates under its own set of circumstances and in its own environment. Even identical machines of the same age working in the same application will have a different wear profile. Now, it's important to understand that the absolute wear values that the laboratory gives us is not entirely relevant. What is meaningful is how the number has changed from the last oil sample. So we are not just looking at the amount of iron, but the amount of iron for a given time period. We are looking at a wear rate, not a static wear value, because wear is a function of time. And that is why we use trend analysis. So in this example over here, you have 2 engines, engine A and engine B. Both of them have generated 100 parts per million of iron. Parts per million is the unit, one of the units that we use to measure metals inside the oil. So both have generated 100 parts per million of iron. In the case of engine A, it has generated 100 parts per million after 500 hours of oil use. So if we were to normalize that, that would be the equivalent of 20 parts per million every 100 hours. If we then look at engine B, which is also generating 100 parts per million of iron, but it is doing so after only 100 hours. So if we normalize that, that basically means that it's generating 100 parts per million every 100 hours. So that by the time we got to 500 hours, it would be 500 parts per million of iron, and that would be a serious problem. So it's not just about the number, it's very much about trend. So trend analysis is possibly the most important aspect of interpreting oil analysis results. The trend analysis is used to basically highlight non-conforming values in the test results, but experience is used to tell if that shift in trend is significant or not. And that requires not only an experienced diagnostician or data analyst with a solid understanding of tribology and chemistry and mechanics, but also someone who is familiar with the customer's equipment, operation, and also maintenance practices. So here's a great example of how oil analysis isn't just about the numbers, it's about patterns and relationships, just like life. So let's say we detect an increase in the amount of copper in an engine oil sample. That alone doesn't tell us very much, but when we look at companion elements, it starts to tell us a story. If there are no other metals with the copper, it might be oil cooler core leaching, which is a very common thing to see inside engine oils, especially after an overhaul, or even if a customer has changed from one brand of oil to another. If we see copper with sodium, potassium, and boron, we're likely dealing with an internal coolant leak. If we see copper with zinc, lead, and tin, it could point to bearing wear. And if we see, for example, aluminium and nickel with copper, we might be looking at contamination from an anti-seize compound, especially after an overhaul. So trend analysis and elemental families help us move from, let's call it raw data to root cause. And that's how oil analysis ultimately becomes a diagnostic tool and not just a bunch of lab results and numbers. Ratios of wear metals are also considered when we are looking at detecting abnormal wear. So this slide shows why interpreting wear metals in context is so important. So on the right, I'm showing you a typical tri-metal bearing. The outer shell is steel, the mid layer has copper and lead with a soft overlay, which is babbitt, and that usually also contains things like lead, tin, maybe a bit of bismuth or antimony. So that's what the bearing construction, a typical bearing construction would look like. On the left, I am representing two results from two different oil samples. The first one on the left side of the chart shows 50 parts per million of iron and 10 parts per million of lead. That's a healthy ratio, suggesting typical benign bearing and shaft wear. But look at the second set. Iron has dropped to 35 parts per million, while the lead has spiked to 25 parts per million. That imbalance between those two metals is a red flag. It suggests that the soft babbitt overlay, which is very rich in lead, is wearing faster than the steel components. If we were only looking at the absolute lead number of 25, it might not alarm you. But when you compare it to a lower iron level, the ratio reveals a potential issue. And this highlights one of the biggest dangers of using static wear limits in oil analysis, as that they often only consider the laboratory results in isolation. You need both knowledge of component metallurgy and an understanding of the metal ratios to accurately interpret wear data. So in terms of the techniques used to detect wear, these are probably the more common techniques that most commercial oil analysis laboratories would use. There's spectrometric analysis, which measures the concentration of elements associated with wear metals, contaminants, and additives in the oil. So these would be things like iron, copper, chromium, aluminium, calcium. The vast majority of spectrometers can measure anything from 30 to up to 40 different elements. And these are measured, as I've mentioned before, in parts per million. And this technique measures very, very small particles, usually below 8 micron in size. So to give you an idea of how small that is, if you were to take one of your hairs and cut it in half, the average diameter of a hair follicle is 80 micron in size. We are detecting 8 micron and below in size, so incredibly small. Then there is the PQ index, or particle quantifier index, and this measures the total ferrous content inside the oil sample, irrespective of the particle size. So when it comes to wear, you're not just measuring one thing, you're measuring wear, but in different sizes that might be generated inside a mechanical system. And the PQ is often compared to the spectrometric ion reading, because a lower PQ than ion ratio could suggest few large particles are being generated, which we would consider to be normal, whereas a rising PQ with a stable or low ion value could indicate larger wear particles are being generated, or larger wear debris. And this may then prompt further tests like the following test, microscopic particle examination. So in this, we filter the oil through a membrane of known size, and we examine the debris that is removed from the oil sample underneath a microscope to basically assess wear, contamination, and potential failure severity. And then finally, you have analytical ferrography. Now, this is a much more sophisticated version of the MPE, or microscopic particle examination, as this technique involves observing and categorizing particle size, shape, and color, as well as surface texture under much higher magnification, usually using an optical ferroscope, which has the ability to magnify a wear particle up to 1,000 times. And the particle's composition basically indicates its source, and the particle shape or morphology reveals how it was generated. So analytical ferrography is something that generally only gets done when it's part of a failure investigation. Second function, detect oil degradation. Lubricants don't last forever. Over time, they degrade through a variety of mechanisms like oxidation, thermal breakdown, microdieseling, additive depletion, and more. And these degradation modes affect the chemical and physical properties of the base oil as well as the additives, which in turn reduces the lubricant's ability to do its job and perform its function. Functions like reducing friction and wear, removing heat, acting as a structural material. In the case of a hydraulic system, transmitting power, as well as managing contaminants like air, water, and combustion byproducts. All of these functions are negatively affected when the oil is degraded. Now, these degradation mechanisms all produce different types of identifiable physical and chemical characteristics that can be detected by oil analysis, either directly or through their byproduct or effect on the oil. So for example, in the case of oxidation, this would reveal itself with an increase in viscosity, an increase in acid buildup and sludge formation, as well as a reduction of the total base number or alkalinity reserve of the oil. So that's just one example. So by understanding these degradation modes and knowing what to look for, we can catch problems early and extend the life of both the lubricant and ultimately the asset that it's protecting. And these are the most common techniques used in commercial laboratory. So tracking viscosity trend is essential, because a rising viscosity could signal oxidation, while a drop in viscosity often points to a shear-related additive loss, for example, in viscosity index improvers, or it could be as a result of incorrect topping up. Both can indicate base oil degradation and contamination. Then you have TAN, or total acid number. This measures the acidic compounds formed as a result of oxidation. So a rising TAN can also indicate antioxidant depletion, which makes it a key marker for oil condition and serviceability. Then you have infrared analysis. This one is often called the oil's fingerprint, because it uses infrared light to detect oxidation by identifying chemical changes in the base oil. So it basically shows how oxidation changes the hydrocarbon backbone of the oil into different types of byproducts. And it's those byproducts that we can measure using infrared spectroscopy. Then you have slightly more advanced techniques like the ruler test or remaining useful life. This measures how much antioxidants are still present inside the oil, and this helps predict lubricant life and optimize oil change intervals based on depletions. Ruler is generally only done on really big oil systems like turbine oils or large compressor oils. And then finally, you have MPC, or membrane patch colorimetry. And this test basically measures the potential for varnish formation in the lubricant as a result of oxidation. It does this by quantifying the amount of, let's call them insoluble color bodies present inside the oil. So those are the main laboratory techniques that most labs use for detecting oil degradation. Now, the third major function of oil analysis is to monitor contaminant levels. So contaminants can directly damage the machine being lubricated, causing abnormal wear on internal components. But they can also be indirectly damaging by degrading the oil itself, which reduces its ability to protect and lubricate the system. So let's take a look at where contaminants come from and why we think they are such an issue. So contaminants fall into two broad categories, internal and external. It's very self-explanatory, and that talks about where they come from. So internal contaminants are generated within the mechanical system. So examples are combustion byproducts like soot or fuel dilution or an internal coolant leak. So why don't we like this? Well, fuel dilution lowers the viscosity of the oil. It weakens the film strength. It has the ability to wash oil off cylinder walls. It leads to increased top end and also bottom end wear inside an engine. Soot raises the oil's viscosity. It accelerates oxidation. It depletes additive. It's also very abrasive. Internal coolant leaks, especially when the coolant contains glycol, that can increase the viscosity. It can trigger oxidation. It causes acid formation and usually corrosive wear of bearings. As for external contaminants, these are substances that come from the environment that really shouldn't be inside the mechanical system. So dust or dirt, it's abrasive and accelerates component wear. Water causes corrosion and rust, as well as additive depletion and base oil degradation. And air, yes, believe it or not, air can be a very, very nasty contaminant. It can lead to foaming, microdieseling or adiabatic compression, oxidation, additive depletion, and reduced heat transfer. So all in all, can be quite nasty. So while the primary functions of oil analysis are to detect abnormal wear, oil degradation, and contamination, these lead to several other secondary benefits, let's call them that. So for example, oil analysis can also detect impending failures. These are situations where wear or damage accelerates very suddenly over a short period of time. So an oil sample might reveal severe changes, even though the previous oil sample looked completely normal. Now, this is different from spotting gradual abnormal wear, because in many failures, most of the damage happens right at the physical point of failure. And that's why oil analysis is so valuable. It offers a critical window to act before failure strikes, reducing both repair severity and cost, because most of your repair bill in the case of a failure is going to go to fixing the initial or primary point of failure. Verify the oil in use, a very important function of oil analysis. So when an oil sample is submitted to the laboratory, the customer is asked to fully identify the oil being used. So that is the brand of oil, the grade of oil, and the series. Often, unfortunately, this becomes a case of what oil do you think you are using? And the answer can be very surprising. Over 20% of the samples that we test are mixtures of oils or completely different to what the customer thinks is in use inside his machines. If the oil in use is not what the customer expects, this may point to several underlying issues. In the most serious case, the oil might not even be suitable or even recommended for that particular application. Incorrect oil use could indicate a problem with maintenance practices. Mixtures of oils may highlight the need for better training of the staff who are involved with doing the servicing. And look, while certain mixtures might be technically acceptable, they still raise important concerns about consistency and process control. Then alternative brands or grades may be acceptable in one application, but not necessarily in another. And in certain cases, and especially under OEM warranties, using a non-recommended lubricant may result in a denied claim if a failure occurs, and that is something we see quite often. So a very important function. Okay, moving on to the next one. So oil analysis also allows us to optimize oil drain intervals, and the key word here is optimize, not how far can I push my oil. So let's use a historical earth-moving equipment. When I started in the oil analysis industry about 30 years ago, most engine manufacturers recommended a blanket 250 engine oil drain interval. It didn't matter the engine type, the model, the application, or the environment. You could have a bulldozer building a dam in the Kalahari, or you could have a loader doing light work in Nairobi. It didn't matter. Both got exactly the same schedule. One size fits all. But we know better now. With oil analysis, we can adjust the oil drain interval or the service interval to match the actual operating conditions. So in a light duty or clean environment, intervals may be safely extended. However, if you are working in a harsher or high load application or environment, we may need to shorten the oil drain interval to protect the asset. Now, yes, shortening intervals does mean an increase in costs like oil and labor, but if it extends engine life and prevents failure, the return is worth it. And this is a mantra I often use with customers. Count the cost of lubrication, not the cost of the oil. The goal isn't just longer intervals, it's smarter, condition-based decisions. Okay, so let's talk about equipment overhauls. Equipment overhauls are often scheduled using empirical time intervals, whether that be hours, kilometers, or even calendar based. And these are usually derived from historical averages. So let's say, for example, if the average time for a transmission to fail is 10,000 hours, then it seems logical to try and either schedule a replacement or repair just before 10,000 hours. But the problem is averages are just that, average. This approach won't catch early failures, and it may also result in replacing components that still have remaining useful life. Oil analysis gives you the opportunity to make that decision based on condition. So by performing non-destructive, non-invasive tests and reviewing the historical data, we might be able to defer an overhaul when everything is still within spec, or bring an overhaul forward if the results are trending critically. Avoid loss of production. This is probably one of, in my opinion, probably one of the biggest things when it comes to the biggest benefits of an oil analysis program. So an oil analysis program or any maintenance activity for that matter must be able to justify itself financially. The cost of labor and materials is pretty easy to calculate. Oil analysis detects a fault. You schedule a repair, you order the parts, you make the manpower available to carry out the repair, and everything works out nicely. These are all easily quantifiable parameters. And even the cost of failure can be calculated had the problem not been highlighted by an oil analysis program. But what would be the impact on production if a production line had gone down for 2 days? Or if the prime mover in a mining operation was in the workshop for a week? What would happen if a quarter of the buses were off the road due to unscheduled repairs over a public holiday? So what would be the repercussions of your company not completing the job on time? Now, unlike parts and labor, production loss isn't a fixed line item. It varies with time, asset criticality, and system interdependencies within any organization. And it makes it harder to quantify, but it's often the largest driver of cost, and avoiding it is where oil analysis delivers its greatest value. And ultimately, the main purpose of oil analysis is to save money, and that's what it comes down to, reducing operating costs and making the organization more profitable. Every benefit that we've discussed, from detecting wear, preventing failures, optimizing service intervals, avoiding unplanned downtime, all of it contributes to that bottom line. A well-run oil analysis program can deliver a return on investment of 10 to 1 or more. So for every $1 you spend on oil analysis, you could be saving $10 in unscheduled repairs, unplanned downtime, and unexpected failures. Now ask yourself this: where else can you find an investment like that in today's world? Thank you.
Thank you. Thank you very much. That was really nice and straight. One or two questions before we can get Miriam taking us to some questions that are maybe jotted by our participants. In your opinion, should organizations now move away from the way they just use-based oil changes and rely specifically or solely on condition-based driven oil change? And what could be the trade-off?
I'm going to say yes, they should move away from strictly use-based oil changes and shift towards condition-based oil changes wherever practical, because condition monitoring, or at least oil analysis, tells you what's actually happening with the oil. So you might be draining good oil when you could still keep it in use for longer, or you, even worse, leaving degraded oil in use when you should be draining it sooner. So the trade-off is really much cost and effort. So effort to take the sample and implement an oil analysis program, and then of course the cost to actually do it. But I do believe, and we do see it, we see a number of people with engines. It's a bit of a gray area. We see people extending the oil drain with engines, but generally we have a number of customers who have hydraulic systems, big hydraulic systems that take 3 to 4 to 500 liters of oil. The recommended oil drain interval is around about 2,000 hours, but they will try and extend that to 3,000 or 4,000 hours, of course, putting other things in place, not just oil analysis. They'll put additional filtration, supplemental filtration. They'll put breathers onto the system, and they will use oil analysis as a tool to monitor that process. So the idea is that you do oil analysis so we can tell you when the oil is degraded or when there are contaminants, because then you need to take action to remove them. Lack of technical expertise, I totally agree with 100%. And it's so important. So oil analysis can only go so far. I've got a team of engineers and chemists who will take a look at those results and they'll turn them into something tangible. So we will point out things to you. We will say the viscosity is high. It could be as a result of soot. Check valve clearances, check for excessive blow-by. But ultimately, what it comes down to is whoever receives that report needs to be able to look at it and know what to do with that. And that's where we see a huge gap in industry. And it's one of the reasons we embarked on doing training for our customers. So, basically explaining to them, number one, what oil analysis is, but also showing them how to take the sample correctly, why you've got to do it like this. What do all those numbers mean on the report? What do you do with that? How do you take it further? But yes, I agree with that. Technical expertise is a big issue. Inconsistent monitoring practices, it depends on which way you look at that. So the vast majority of commercial laboratories have very similar equipment because we are looking at measuring the same things. But even within those laboratories, there are going to be slight variations in terms of what it is that you basically are able to offer the customer. So I'm not quite sure if that's what people mean by inconsistent monitoring practices. Limited access to advanced technology. I don't know if advanced technology, it might work in certain situations, but not necessarily in others. So advanced technology for me would be the equivalent of maybe using online sensors, which, for telemetry, which, I mean, a lot of brand new equipment comes with that. But I mean, there are lots of other instruments that you can basically add onto your machine that the OEM will sort of guide you with. But it still means you need to do something with that data. It's all very well that you spend millions of rands putting all these devices on the machine. How do you translate that? What do you do with that? How does that translate to, okay, I now need to do step A, B, C, and D. So advanced technologies might work in some environments, but not in others.
Awesome. And also in terms of looking at the inconsistent monitoring, I think some people don't have, specified interval of sampling, changing the oil or checking the condition. And also even the equipment, like how do you get the sample from an equipment? Maybe they don't have the right equipment. So that also can be a challenge.
Yes, I agree with you. I agree 100%, Doctor.
Okay, so I'll send back now to Miriam, who can take us through on the question and answer so that Stephen can continue answering them.
Thank you, James and Stephen, for that session. Stephen, there are a few questions for you here. One is about transformer oils. Kenneth is asking, sorry, what kind of tests are done on power transformer oil? How do you know if it's deteriorating? And after how long should it be changed, especially in higher rating transformers used on substations?
Okay, well, unfortunately, I can't really answer that because I deal with lubricating oils, not transformer oils, which are insulating oils. But my limited knowledge, because we do test transformer oils, you are looking at, people call it MAD testing, as in MAD, M-A-D. So it's moisture acid dielectric. So the vast majority of people in South Africa, especially when you're looking at high voltage, they will do that probably once every 3 months. And then based on those results, they will then take it one step further, and they will then start looking at dissolved gas analysis to pick up deterioration of the paper inside the transformer. They will start looking at trying to measure corona gases, things like methane. They will look at interfacial tension. So it's pretty much those basic tests that then drive the more advanced tests. And based on that, then they will either purify the transformer oil to remove the moisture, or in the case of PCBs, you really have to just change the oil. I mean, it's very rare to see transformer oils with PCBs, but it's very, very toxic, and we still do see it every now and then. But if you're willing to, if Kenneth is willing to drop me an email, I can certainly share more information that I have on our transformer analysis and the program that we run in South Africa.
Awesome. We will pin Stephen's email address on the chat, so be on the lookout for that, Kenneth, and any other person who might want to reach out to Stephen directly. The other is a comment from Ahmed. He's saying he's enjoying the webinar from Canada. Thank you so much for that positive feedback, Ahmed. Nicodemus was asking if you could display the first slide on wear analysis, but I think, Stephen, you would be willing to share the slides after this, the presentation, right?
Yeah.
Okay,
certainly.
so awesome. Yeah, so that will be sent to you, Nicodemus. We will also pin our emails so that you can reach out, so that it's easier to send. The other question is from Peter. He says, I normally use used oil on my chainsaw to cut costs. Is this bad for my machine?
I wish I could tell you I don't own a chainsaw. The problem with something like that, you can use used oil if you know what's inside it. So for example, if you have, and from where? So if it's gear oil, it might have EP additives inside it. If it's a used engine oil, you might find that, let's say, for example, the engine had a problem with fuel dilution and it has a lot of diesel inside it. So it really depends on what contaminants are inside that oil. That would ultimately drive, if it's going to cause any damage to your chainsaw.
Awesome. We have a long question here from Martin. He's saying we are a CMMS software provider and one of our customer reached out to ask for assistance. How do they visually detect poor or low quality oils put in their generators? This is the context. The client has 80 locations in the country, each with a backup generator. Genset ratings vary between 15 kVA to 40 kVA. I'm sure, Stephen, you're catching up on that, depending on the size of operation at the location. This issue has led them to do preventive maintenance every quarter instead of the previous half-year interval. This was realized after about 6 failed. Average PM activity per generator costs ranges between $600 to $800 per quarter. So I think his question at the beginning was, how do they visually detect poor or low quality oils put in their generators?
You know what? That could be a presentation by itself. And I think it comes down to identifying what people mean when they say quality. So that's probably the number one question I get asked by customers. Can you tell me how good my oil is? Is this a quality product? And my response is, compared to what? I can measure the physical and chemical characteristics of the oil, but I cannot tell you what it's going to do once it is in use. That is the realm of performance testing and the domain of people like the API, ASEA, ILSAC, who work in collaboration with testing organizations like the ASTM, the OEMs, and the lubricant manufacturers. And performance testing, you're now talking about millions and millions of rands to basically do, because that's ultimately the performance test. However, on site, it's very, very difficult unless you've got an instrument on site. They can start off by looking at viscosity. So something as simple as viscosity. Is it too thin? Is it too thick? If you can't do any testing on site, stick to a reputable oil supplier. Do not try and cut costs, because we see counterfeiting all through Africa. A lot of people out there are getting very, very smart. They're doing counterfeiting. And this is not just small operations, small little shops on the side of the road. I'm talking big operations. These people have become very, very sophisticated with their branding of the bottles, and you ultimately don't know what's inside. So if you're asking me, how can you tell if it's a quality oil? You really can only do that with testing. Short of doing a visual, I mean, believe you me, if I could look at an oil and just with my eyes, I could tell if it was a quality oil, I would be a multi-millionaire. But unfortunately, you need to test the oil and you need to look at the physical and chemical characteristics and compare that to the new oil values to see if this is a quality product and if it's doing its job. You also have reputable oil companies that make formulation mistakes. And we see that quite often as well because of the large volumes of samples that we basically get. There's a slight differentiation in a formulation from one batch to another. That could have an impact on your equipment, especially in high temperature, full load applications. But ultimately, you need to be able to test that oil to see what's inside.
Awesome. We have pinned Stephen's email. Martin, just in case you would want to follow it up further with Stephen, you can always reach out to her. Ahmed has about 4 questions, so we are going to go through them quickly. The first one is, what are the quick tests on site on HDEO? I'm thinking this is heavy duty engine oils. I think he's asking, what are the quick tests to be done on site?
It depends on how much money you have. You can go to a company like Kittiwake, and you can get an instrument provided you're willing to part with I don't know, $200,000. I mean, we actually put labs on site, but you also get on-site laboratories. Literally, it's something that you could put on a desktop. You put an oil sample in and you can test, but again, you're now probably looking at about 1.5 million rands. In terms of on-site, here's the problem. With a piece of paper, a visco stick, and a magnet, I could probably diagnose most problems on an engine. But it comes down to being able to interpret those results. So, there was an old test that they used to use called the blotter test. You take a small drop of used engine oil, you put it on a piece of blotting paper. You would take a look at it, and the way it spreads out can tell you a number of things. So if you see a yellow halo, it could be oxidation. If you see rings, it indicates fuel dilution. It doesn't tell you how much fuel dilution, but it tells you that there's fuel dilution. If you see that it's not dispersing correctly, it's probably overloaded with soot. So there's things like that. What I would encourage people to do on site is cut open your oil filters. That is one of the biggest things that people do not do, and it's one of the easiest ways to prevent engine failures. Cut open your oil filter, get used to seeing what's inside the filter media. Open up that paper, get a fridge magnet, put the magnet underneath. If it moves, it's still. Get used to seeing the particles, shapes, and size. If you can see big particles with the naked eye, you've got a problem. If you see shiny stuff that looks like gold, you've got a problem. It means that it's copper and it's probably coming from a bearing or a thrust washer. If it doesn't move with the magnet, It could be either aluminium or it could be lead. You can go to the chemist and you can buy something called sodium hydroxide. If you put it onto aluminium, it fizzes like Enos. So there's all these very sort of, let's call them bush oil analysis techniques that you can implement, but it ultimately, it hinges on being able to know what to do with that visual comparison. We sell something called a Rio stick, which we developed, which is a simple piece of plastic. You put your used oil in one channel, your new oil in the other, and you sort of tip this piece of plastic up and you look at how the used oil runs against the new oil. If it runs faster, it means your oil is too thin. It could be fuel dilution, or someone could have topped it up with hydraulic oil. If your used oil flows, if it takes longer to flow down, it means that it's too thick. It could be that it's heavily sooted. So all you know is that it's too thin or too thick, as opposed to what it should be, but it doesn't tell you why.
Awesome. Thank you for that, Stephen. I think because of time, we're just going to take a few more questions. And for any other person who might have follow-up questions, feel free to reach out to Stephen. But we're going to take about 2 or 3 more questions, which I think are really key, Stephen. And one is, what tests are done on additives to confirm their quality before using them?
Nothing, again, that's performance testing. So I can, what we're measuring with oil analysis, I'm looking at elements. So the spectrometric analysis looks at elements. It's not giving you an indication of the compound. So I, for example, would measure calcium. What does calcium mean? It means nothing. Calcium is an element within a broader chemical concoction. It could be a calcium sulfonate, which is a detergent additive inside the oil. But a lot of that, in other words, how do you treat the base oil? What percentage do you use? That kind of stuff is done by the oil companies themselves. And ultimately, they will buy a full-on additive package from the likes of Lubrizol or Infinium. And it's usually the additive companies, believe it or not, who actually guide the lubricant manufacturers into, you use this additive package with this base oil to get to this API rating to conform to the following performance specifications. So that is very much the realm of performance testing.
Thank you for that. I think one last question so that we can wrap up. This one says, I have a planetary gearbox driven by a hydraulic motor. The planetary gearbox uses gear oil of EP220 and the hydraulic motor uses Azola 100. There has been a constant issue with low viscosity on that of the gear oil. Any idea what's causing this, since it happens constantly?
It could be a myriad of different things. Depending on how the system is configured, you could be looking at oil transfer. So you could have the hydraulic oil transferring into the gearing system. That's the first thing. Topping up. We often see this with people who top up with the incorrect oil. That they'll take a look at it and they'll say, okay, well, a little bit of this, a little bit of that, we'll top it up. It should be fine. No, it's not. Hydraulic oil and gear oils have very, very different additive packages. But if you're constantly seeing a dropping of viscosity, and again, it also depends on how much the viscosity is dropping. If it's an industrial ISO 220 EP gear oil, you're not really going to have a lot of, for example, viscosity index improver additives that might shear as a result of the gearing action. So it's not going to be additive depletion. My bet is on some form of oil transfer, whether it's through a duocone seal or a labyrinth seal, if the two systems are somehow connected but separated with a sealing system, or someone is topping up something else inside the gearbox.
Okay, thank you for that, Stephen. In the interest of time, that's all the questions we're able to tackle for now. Feel free to, again, reach out to Stephen with any additional question you might have. James has included in the chats that for everyone who registered for the webinar, you're going to receive the slides. So be on the lookout for that. I'll quickly hand it over to James, just in case he has any closing remarks and also updates for upcoming webinars.
Yeah, thanks so much. Thanks, Stephen, Lumley. Thanks, Miriam. I think time has really run, but we are grateful for the time that we've had. I think it was very, very informative. The people with the other questions, we will send the questions to Stephen Lumley and also your email addresses if she can directly answer your questions. For the next webinar, be on the lookout. We will advertise it. That will be towards the end of next month. Fortunately, we've started a YouTube channel where these webinars will be, of course, posted there. So already last webinar is already there. And permit us to send you the details through your emails because we have your emails now. But for now, I think I want us to stop there. I want to thank Stephen for a very informative session, and we'll call you back. I think you have elicited quite some good reaction, and I think everyone wants to hear about maintenance, especially when you correlate it with lubricants. So I think in a number of months, you should be back here on the dock, and we are grateful. Thanks, Miriam, for putting up the session. And there are other team members who are behind the scene, like Peace Wanjiko and Patience, and the others. We thank you very much. For the participants, thank you for honoring and being part of this session. I believe we've learned quite a bit of something, and I pray that the next session will be even better. So we pray that we have a nice evening. May God bless you, and see you next month.
Bye, everyone, and God bless. Take care.
God bless you.
Thank you.
Thanks.
Bye.